Welcome to the peaceful space of sleep-friendly science, where tonight we'll drift to the edge of time itself, to the quiet moment just before our universe was born. Tonight, we're going to gently explore one of the deepest questions we can ask: what happened before the Big Bang? As you get cozy for this cosmic journey, if you enjoy these quiet explorations, a gentle tap on the like button is always appreciated. I'd also love to know where in the world you're unwinding from tonight. It's a quiet joy to imagine us all drifting together from different corners of the globe. But for now, there's no need to rush. The universe's oldest secret is in no hurry. We'll simply float toward that first, silent point and wonder together about the spark that ignited everything. Now settle in, take a deep breath, and let the soft sounds of the universe guide you as we begin tonight's journey into the unknown. Section 1: The Edge of Knowing. Before there was time, before there was space, before a single star had ever flickered into being, there was, well, that is the great question, isn't it? Our story doesn't begin with a bang, but with the profound, unimaginable stillness that came before it. To even speak of a before is a challenge, for the Big Bang wasn't an explosion in space, it was the beginning of space and time themselves. So how can we talk about a moment before time existed? This is where our journey becomes less about finding an answer and more about exploring the beautiful, mind-bending possibilities that physics offers us. It is a place where science touches philosophy and where the laws of nature as we know them begin to fade into a gentle, shimmering fog. Imagine yourself floating, not in darkness, but in a state that has no light to contrast with. You are in a void that isn't a void, for there are no dimensions to define it, no up or down, no left or right. It has no duration, for there are no clocks to tick and no events to measure the passing of moments. It is a state of pure potential, a silence so complete that the concept of sound has yet to be invented. This is the edge of knowing, the very limit of our language and our physics. Asking what came before the Big Bang is a bit like standing at the North Pole and asking, which way is north? From that point, every direction is south. The question itself dissolves because the framework it relies on, in this case, the linear, forward-moving direction of time, has ceased to exist. Our human minds are wired for causality. We crave beginnings, middles, and ends. We think in stories, and every story needs a first page, a first cause, a first spark that sets everything else in motion. It is a deeply ingrained instinct, this search for an origin. We look at the vast, intricate cosmos and assume that something must have preceded it, something must have lit the fuse. But the universe, in its quiet, indifferent grandeur, does not necessarily operate on the narrative principles we find so comforting. This first page might be the book itself. The Big Bang wasn't a firecracker lit in an empty, pre-existing room. It was the room itself, the walls, the floor, the ceiling, the very air within it all springing into existence from a single, infinitesimal point of potential. There was no outside to look in from, no empty stage waiting for the play to begin. The stage, the actors, the audience, and the script all appeared in the same instant. This is the point where our most powerful and elegant theories of the universe, Einstein's general relativity, and the strange, probabilistic rules of quantum mechanics begin to falter. General relativity, the theory that so beautifully describes gravity, the graceful dance of planets, and the silent waltz of galaxies, works magnificently on the largest of scales. But if you rewind the cosmic clock all the way back to the beginning, it predicts a point of infinite density, infinite temperature, and infinite curvature of space to me, a singularity. At this point, the equations break down. They give us answers that are nonsensical, like dividing by zero. It is the universe's way of politely yet firmly telling us you cannot use that map here. The territory is different. Similarly, quantum mechanics, the fundamental theory of the very small which governs the bizarre and wonderful world of particles, struggles to incorporate gravity into its framework. The two great pillars of modern physics, one for the large and one for the small, have not yet learned how to speak the same language when it comes to the moment of creation. This unresolved tension, this quiet disagreement between our best descriptions of reality, is one of the deepest and most tantalizing mysteries in all of science. It means that to understand the origin, we likely need a new kind of physics, a theory of quantum gravity that can weave together the fabric of space-time with the ghostly dance of particles. So, we are left standing at a locked door with a question our science cannot yet fully answer. But this is not a point of failure. It is a point of profound and humbling wonder. It is the fertile ground where imagination and rigorous speculation can gently take flight. If our current laws of physics break down at the beginning, perhaps that means there are other, deeper laws we haven't yet discovered. Perhaps the Big Bang wasn't an absolute beginning from nothing, but merely a transition, a moment of metamorphosis from one state of being to another, a state with rules and properties we can barely begin to conceive. Let your mind drift with this idea for a moment. Feel the comfort in not knowing. In a world that often demands answers, certainty, and immediate explanations, there is a quiet, meditative peace in accepting a mystery. The origin of our universe is perhaps the greatest mystery of all. It invites us not to conquer it with facts, but to approach it with a sense of awe. It is a quiet reminder that we are part of something so vast, so ancient, and so fundamentally strange that our most advanced understanding is but a tiny, flickering candle in a limitless darkness. We are a brief, curious thought in an eternal, silent mind. We can feel the pull of the question, can't we? It hums in the background of our quietest moments, a gentle, persistent query from the depths of our own consciousness. What set it all in motion? What was the nature of that initial, timeless, spaceless state? Did it require a cause, or could something truly, magnificently arise from nothing? These are not just scientific inquiries, they are philosophical, almost spiritual in their weight. They touch the very core of our desire to understand our place in the cosmos, to find meaning in our fleeting existence. And as we float here, on the very precipice of time, let us not be anxious for a definitive answer. Instead, let's simply be with the question. Let its immense weight and its beautiful lightness fill your thoughts. The story of the universe may not have a before that we can ever comprehend, but it does have a beginning that we can explore. A moment when that silent, perfect potential began to unfold into the grand, sprawling, stardusted reality we now inhabit. Let's move our focus away from the impossible before and drift closer to that first, singular point. Let's approach the seed of everything, the cosmic egg from which all of existence hatched. Section 2: The Seed of Everything. Let us drift closer now, not with speed, for there is no distance to cross, but with our focus, our quiet intention. We approach the beginning, the classical singularity. This is the seed from which our entire cosmos would eventually sprout, the single point from which all of reality would be born. Try to picture it in the theater of your mind, though all our earthly metaphors will ultimately fall short. Imagine the entire universe, every star you have ever seen twinkling in the night sky, every galaxy the Hubble telescope has ever photographed, with its swirling arms of gas and light, every planet, every ocean, every mountain, every living creature, you, me, the very thoughts floating through our minds, and the immense fabric of space that separates Uzel of it, the entirety of existence, compressed into a region of space so small that it is functionally a point with no dimension at all. It is a place where the very idea of size loses its meaning. In the precise and elegant language of Einstein's general relativity, this singularity is a point of infinite density, infinite temperature, and infinite curvature of spacetime. It is a state hotter than the core of a billion suns, denser than a crushed black hole. It is the ultimate compression, the final mathematical point to which our best theory of gravity leads us when we run the clock of the universe backward. But let us not be intimidated by the word infinity. In physics, when our equations present us with an infinity, it is often a gentle sign, a quiet whisper from the mathematics itself, telling us that our theory has reached its limit, that there is a deeper, more fundamental truth we have not yet grasped. So, as you rest here, think of this singularity not as a jagged, violent, chaotic point, but as a place of profound and perfect potential, a place of absolute simplicity. In this initial state, there was no chaos. There was a state of perfect, unimaginable order. It was a single, unified entity where the four fundamental forces of nature that govern our universe today, gravity, electromagnetism, and the strong and weak nuclear forces, were not separate. They were merged, unified into one single, elegant, and perfectly symmetric superforce. There was no distinction between matter and energy, between a particle of light and a particle of substance, between the fabric of space and the flow of time. Everything was one. It was the universe in its most elemental and pristine form. You could imagine it as a single, perfect thought before it fractures into a million words. Or perhaps as a flawless, transparent sphere of glass that contains the light of every possible color, not yet separated and scattered by the prism of existence. You were there, in a sense. The atoms that make up your body, the carbon, the oxygen, the iron in your blood, the calcium in your bones, all of it was present in that initial state. Not as the atoms we know, not even as the protons and neutrons that form their nuclei, but as pure, undifferentiated energy, a boundless potential held within that infinitesimal point. The possibility for every story, every life, every sunrise, and every quiet moment of reflection like this one was held in silent incubation within that cosmic egg. It contained not just the blueprint for a universe, but the universe itself in its most concentrated and perfect form. This idea fundamentally challenges our intuition, our everyday sense of how the world works. How can so much, the entirety of everything, exist in so little, a space with no volume? But in this primordial realm, the rules of our waking experience do not apply. The very concepts of inside and outside are rendered meaningless. The singularity did not exist in a place, it was the place. It was the origin point from which all locations would eventually be measured, the central node from which the map of reality would be drawn. It was the moment from which all clocks would eventually start ticking, the zero on the ruler of time. As we hover here, in this conceptual, timeless space, let us appreciate the profound stillness. For an unknown durationer, perhaps in a state entirely outside of duration altogether, this silent potential simply existed. It was a universe holding its breath, poised on the brink of becoming. There was no movement, for there was no space to move through. There was no change, for there was no time to measure it. It was a state of pure being, pregnant with the explosive possibility of all that was to come. But this state of perfect symmetry, of unified and simple elegance, could not last. In the grand narrative of the cosmos, perfection is often a fleeting and unstable state. Imagine a pencil balanced perfectly on its sharpest tip. It is a moment of perfect equilibrium, but it is also exquisitely fragile. The slightest nudge, the faintest whisper of a quantum fluctuation, can cause it to fall into a less symmetric, more complex, and more interesting state. The initial singularity was that pencil, balanced on the precipice of existence. What was that nudge? What unseen force or inherent instability caused this seed of everything to begin its magnificent unfurling? Scientists still debate the precise mechanism, exploring theories that lie at the very edge of our understanding. But they agree on what happened next. Something disturbed that perfect, silent equilibrium. The universe began to expand. Not like a conventional explosion pushing matter outward into a pre-existing void, but as an expansion of space itself. The very fabric of reality, once a single point, began to stretch, carrying everything with it on a silent, outward journey. This was not a violent event, not a chaotic rupture. In its very first moments, it was something far more rapid, more profound, and more exquisitely orderly than we can easily imagine. It was a graceful and exponential swelling, a moment that would smooth out the universe and set the stage for everything that followed. It was a process known as cosmic inflation. So, let us now leave the silent, perfect seed behind. It has served its purpose as the vessel of all potential, the quiet womb of creation. Now we will bear witness to the first action the universe ever took. The first deep breath. A breath that would inflate a space smaller than a proton to a size vaster than a galaxy in a fraction of a blink of an eye. The stage was set, the potential was there, and the universe was about to awaken from its timeless slumber. Section 3: The Great Expansion. From that state of perfect, silent potential, the universe began to stir. It was not a shattering, not a violent rupture, but something far more graceful and profound. It was an unfurling. The single point that contained everything, that impossibly dense seed of reality, began to expand. But this was not the kind of expansion you might imagine from your earthly experience, like the debris from an explosion flying outward into an empty room. There was no empty space for it to expand into. The expansion was the creation of space itself. Every new millimeter of reality, every new dimension of existence, was being woven into being in that first, fleeting instant. This initial, breathtaking period of expansion is known to scientists as cosmic inflation. It was the universe's first deep breath, and it was astonishingly, incomprehensibly rapid. In a sliver of time so small it makes a nanosecond look like an eternicial duration on the order of 10 to the power of minus 36 seconds, the universe swelled exponentially. A region of space far, far smaller than a single proton was stretched to a size larger than our entire Milky Way galaxy. It was a silent, perfect swelling, a smooth and seamless expansion of the very fabric of reality. This may sound as though it violates Einstein's great cosmic speed limit, the speed of light, but it does not. The rule is that nothing, no object with mass, can travel through space faster than light. Inflation was different. It was space itself that was expanding, carrying everything along for the ride, like a current in a cosmic river. Imagine drawing two tiny dots on the surface of an uninflated balloon. As you begin to inflate it, the dots move away from each other, not because they are crawling across the rubber surface, but because the surface itself is stretching between them. From the perspective of one dot, the other can appear to be receding at a speed far greater than either could ever travel on its own. Our nascent universe, in that first moment, was that balloon, inflating with a speed and grace that defies our everyday intuition. What could possibly have powered such an incredible event? The leading theory, a cornerstone of modern cosmology, proposes the existence of a hypothetical energy field called the inflaton field that permeated this early, singular state. You can think of it as a kind of latent, potential energy held within the vacuum of the nascent universe itself. This field was in a highly energetic, unstable stadia, false vacuum. It was like a ball perched at the very top of a steep, perfectly smooth hill. It was a state of equilibrium, yes, but a fragile one. The slightest disturbance would cause it to begin rolling down to a more stable, lower energy state at the bottom of the hill, its true vacuum. As the inflaton field began this journey, rolling from its false vacuum to its true one, it released its tremendous stored energy. And that energy is what drove the exponential expansion of space. It acted as a kind of cosmic anti-gravity, pushing space apart rather than pulling it together. For a brief, brilliant moment, the universe was dominated by this single, repulsive force. When this period of inflation ended, as abruptly as it began, the inflaton field decayed. The vast energy it had stored, now spread across a newly immense cosmos, was converted into a hot, dense, and vibrant soup of fundamental particles and radiation. This crucial moment is sometimes called reheating. The universe, which had become vast and cold during its rapid expansion, was suddenly and uniformly filled with the raw ingredients of everything that would ever exist. Quarks, electrons, photons, gluons. It was a searingly hot, energetic plasma. The true, fiery aftermath of the universe's first breath. The stage was now set for the more familiar hot Big Bang story to unfold. The theory of inflation isn't just an elegant story, it is powerful because it solves several deep puzzles about the universe we observe today. One is the horizon problem. When we look out into the cosmos in opposite directions, we see that the universe is remarkably uniform. The temperature of the cosmic microwave background, that faint, ancient afterglow of creation, is almost perfectly the same everywhere we look. In a standard Big Bang model without inflation, these opposite regions of the sky would never have had time to be in causal contact, to interact and reach a shared thermal equilibrium. It would be like finding two people on opposite sides of the earth who had never met or communicated, yet were wearing the exact same outfit down to the last thread. Inflation solves this by proposing that our entire observable universe was born from one single, tiny, causally connected patch. That patch was in thermal equilibrium with itself, and then inflation stretched it to its current, vast size, preserving that uniformity across the cosmos. Another puzzle is the flatness problem. Our universe appears to be geometrically flat on the largest scales. According to general relativity, this is a very special, unstable state. Any slight initial curvature, either positive like a sphere or negative like a saddle, should have been magnified over billions of years. The fact that it is so perfectly flat today implies that it must have been even more exquisitely flat at the beginning. Inflation explains this naturally. The exponential expansion would have stretched out any initial curvature to such a colossal degree that, from our perspective, the universe would appear perfectly flat, much like the surface of the Earth appears flat to a tiny ant standing in a field, even though we know it is a great sphere. So, let your mind rest on this quiet, powerful moment. The universe, born from a seed of pure potential, took a single, monumental breath. It did not explode into being, it blossomed. It stretched the very essence of space, smoothing out the wrinkles of its birth, and in doing so, created the vast, stable, and uniform cosmos that allows for our existence. The very space you occupy right now, the distance between your hand and your face, is a remnant of this ancient, silent stretch. You are living inside the echo of that first, great expansion. And now, with a universe filled with a uniform broth of hot, energetic particles, with a stage vast enough for stars and galaxies to form, another quiet, fundamental question emerges. Where did the rules that would govern this new reality come from? Were they born in that moment of reheating, or were they somehow waiting, woven into the fabric of potential from the very beginning? Section for Forging the Rules. As the inflationary breath subsided, the universe found itself in a new state. It was no longer a silent, singular potential, but a vast, hot, and humming reality. The energy of the inflaton field had decayed, seeding the cosmos with a vibrant, seething plasma of fundamental particles. Quarks jostled with gluons, electrons danced with photons, and for the first time, things began to happen. Interactions, collisions, transformations, the great cosmic play had begun. But for any play to have a story, it needs rules. It needs a script. Where did the laws of physics come from? Were they forged in the fiery crucible of this new beginning? Or were they somehow written into the fabric of existence from the very start? This question takes us to the very heart of the relationship between reality and mathematics. Are the laws of physics the elegant equations that describe gravity, the precise rules of quantum mechanics, the steadfast speed of light? Are they discoveries or inventions? Did we, as conscious beings, simply uncover a pre-existing set of instructions that the universe has always followed? Or are these laws emergent properties, patterns that arise from a deeper, more fundamental chaos, much like the intricate patterns of a snowflake emerge from the simple rules of water crystallization? Let's first drift into the more traditional Platonic view. In this perspective, the laws of physics are timeless and transcendent. They exist outside of the universe, in some abstract mathematical realm, much like the perfect geometric forms in Plato's philosophy. In this view, the universe, upon its creation, simply tuned in to these eternal rules. Gravity didn't have to learn how to pull. It simply obeyed the pre-written law of general relativity. The speed of light didn't decide to be a constant. It was born that way, adhering to a fundamental principle of the cosmos. These laws were not created by the Big Bang. They were the very framework that allowed the Big Bang to happen in the way that it did. There is a strange and beautiful elegance to this idea. It suggests a universe with a deep, inherent order, a cosmos governed by a kind of mathematical soul. The reason our universe is so comprehensible, the reason we can write down equations that predict the motion of planets and the behavior of particles, is because reality itself is fundamentally mathematical. The universe, in this view, doesn't just happen to follow mathematical rules. It is a mathematical structure. We are living inside a grand, self-actualizing equation. But there is another, perhaps more modern and unsettling possibility. What if the laws of physics are not eternal? What if they are more like habits, patterns that the universe fell into as it cooled and evolved? This is the idea of emergent laws. In this scenario, the initial state of the universe, that hot, dense plasma, might have been a place of pure, lawless chaos. But as the universe expanded and cooled, symmetries began to break. Imagine a perfectly still pond. Its surface is uniform, symmetric in every direction. Now, as it begins to freeze, the first ice crystals form. Suddenly, the symmetry is broken. The ice has a structure, a preferred orientation. It has established a local rule. In a similar way, as the universe cooled, the unified superforce began to break apart into the four distinct forces we know today. Gravity separated first, then the strong nuclear force, and finally the weak and electromagnetic forces. Each of these symmetry-breaking events could be seen as a moment when the universe chose a set of rules to live by. The constants of nature, the strength of gravity, the charge of an electron, the speed of light might not have been predetermined. They could be frozen accidents, values that just happen to crystallize out of the cooling cosmos in our particular corner of a potential multiverse. This idea opens up a fascinating, almost dizzying possibility. If the laws of physics are not fundamental, but contingent on the history of our specific universe, then other universes could exist with entirely different laws. Imagine a universe with a slightly stronger force of gravity, where stars burn out in a fraction of the time and no planets can form. Or a universe where the electromagnetic force is weaker, and atoms themselves cannot hold together. Our universe, with its particular set of just right physical laws that allow for the existence of stars, planets, and life, might be an incredibly rare and fortunate occurrence. This is a concept that feeds into the anthropic principle, the idea that the laws of physics must be the way they are because, if they were different, we wouldn't be here to observe them. The question of whether the laws are eternal or emergent is not merely philosophical. It has real implications for our understanding of the universe. If the laws can evolve, could they still be changing today, albeit imperceptibly slowly? Some theories, known as quintessence models, propose that dark energy, the mysterious force accelerating the expansion of the universe, is a sign of a slowly evolving physical law. Furthermore, let's consider the nature of these laws themselves. They are written in the language of mathematics. But why this language? Why is the universe so exquisitely describable by abstract human concepts like numbers, vectors, and differential equations? This is what physicist Eugene Wigner called the unreasonable effectiveness of mathematics in the natural sciences. It is a deep mystery. Is it because our brains evolved to recognize the inherent mathematical patterns of the universe? Or is it because we impose our mathematical frameworks onto reality, and they just happen to be a good fit? As you rest here, surrounded by the quiet hum of existence, let your mind play with these possibilities. Imagine a universe where the script was written before the first actor ever took the stage. A universe of perfect, timeless logic. Then imagine a different universe, one that improvised its own rules as it went along, a grand cosmic jazz performance. Which feels more true to you? Which feels more beautiful? The question of where the rules come from is a reminder that the universe is not just a collection of objects, but a process, a dynamic, evolving system governed by a set of principles that are at once deeply elegant and profoundly mysterious. We are not just living in the universe. We are an expression of its laws. Every breath you take, every thought that flickers through your mind, is a testament to the intricate and finely tuned rules that were forged in the first moments of time. Whether they were discovered or created, they are the silent music to which all of reality dances. Section 5A Universe before this one. The rules of our universe, whether they are eternal or emergent, govern a reality that began with a singular, explosive event. The Big Bang feels so absolute, so definitive, like the first word in a story that could only be told once. It is our cosmic genesis, the ultimate point of origin from which everything we know has flowed. But what if it wasn't the first word? What if it was merely the first word of a new chapter, in a book that has no beginning and no end? This is the central idea behind one of the most profound and ancient concepts in human thought, reimagined today by modern cosmology: the cyclical universe. Let your mind drift away from the idea of a single, linear timeline. Instead, imagine a great cosmic forest. Over vast eons, the forest grows old, the trees become ancient, and the ground becomes still. Then, a fire sweeps through, a great conflagration that returns everything to ash. It is an end, a moment of destruction. But from that ash, nourished by the remnants of the old, new seeds begin to sprout. A new forest rises, different from the one before, yet born from its legacy. The cyclical model of the universe proposes something similar: that our Big Bang was not a unique creation from nothing, but a rebirth, a new beginning that rose from the ashes of a previous cosmos. This idea is not new. It resonates with some of the oldest philosophical and spiritual traditions on our planet. In Hindu cosmology, the universe undergoes an endless cycle of creation and destruction, a cosmic day and night of Brahma, with each cycle, or kalpa, lasting for billions of years. The ancient Stoics of Greece also believed in a cyclical universe, a process they called ekpyrosis, where the cosmos would periodically be consumed by fire and then reborn, repeating its history in an eternal recurrence. It seems that the human mind, when it gazes into the abyss of time, has always been drawn to the comforting rhythm of cycles, a pattern we see reflected in the seasons, in the tides, and in life and death itself. But can this ancient intuition be supported by modern physics? For a long time, the dominant scientific model for a cyclical universe involved a big crunch. In this scenario, the expansion of the universe, driven by the initial momentum of the Big Bang, would eventually slow down due to the gravitational pull of all the matter within it. Gravity would win the cosmic tug-of-war, and the expansion would halt, reverse, and the universe would begin to contract. Galaxies would rush toward each other, merging in a chaotic, fiery collapse, until everything was once again compressed into a hot, dense singularity, which would then bounce and trigger a new Big Bang. It was a beautifully symmetric Idean expanding universe followed by a contracting one, an eternal cosmic breath, inhaling and exhaling over and over. However, a monumental discovery in the late 1990s threw a wrench into this tidy picture. Astronomers found that the expansion of the universe is not slowing down. It is accelerating. A mysterious force, which we have named dark energy, is acting as a kind of cosmic anti-gravity, pushing space apart at an ever-increasing rate. This discovery suggests that our universe is not destined for a big crunch, but for a cold, empty, and ever-expanding future, a big freeze. The idea of a simple bounce seemed to be off the table. And yet, the allure of a cyclical universe has not faded. In recent years, brilliant physicists have proposed new, more sophisticated models that do not require a big crunch. One of the most elegant and mind-bending of these is the conformal cyclic cosmology, CCC, proposed by the great physicist and mathematician Sir Roger Penrose. His theory is a masterpiece of cosmic poetry. Penrose imagines our universe expanding for an almost infinite amount of time, long after the last stars have burned out, long after the last black holes have evaporated through Hawking radiation. In this unimaginably distant future, the universe will be a cold, vast, and almost empty sea of photons and other massless particles. In such a universe, Penrose argues, the concepts of time and distance lose their meaning. Without massive particles to act as clocks or rulers, the universe becomes conformally invariant. It loses its sense of scale. And here is the beautiful, audacious leap. Penrose suggests that this cold, empty, scale-free future of our universe is mathematically identical to the hot, dense, scale-free state of a Big Bang singularity. The end of one universe, stripped of all its complexity and scale, becomes the beginning of the next. The end of one aeon, as he calls it, smoothly and elegantly becomes the bang of a new one. The death of the old universe is precisely the birth of the new. This isn't just a philosophical idea. Penrose and his collaborators have been searching for evidence of a previous aeon. They have looked for faint, circular patterns in the cosmic microwave background, the fossil light from our own Big Bang, which they call Hawking points. These, they theorize, could be the remnants of supermassive black holes evaporating at the very end of the previous universe, their final whispers of energy bleeding through into our own. The evidence is still highly debated, but the search itself is a testament to how seriously scientists are considering this possibility. Another path to a cyclical universe comes from the strange and beautiful world of M-theory, a candidate for the theory of everything. In this model, our three-dimensional universe might be a brain, a membrane-like object floating in a higher dimensional space. The ekpyrotic model, developed by physicists Paul Steinhardt and Neil Turok, proposes that the Big Bang was not a singularity, but the result of our brain universe colliding with another parallel brain. These collisions, they suggest, happen periodically. They are immense, universe-rebooting events that wipe the slate clean and re-energize the cosmos, triggering a new phase of expansion and evolution. Our Big Bang, in this view, was not the first and will not be the last. It was just the most recent in a series of gentle cosmic claps between worlds. Let your mind rest in this vast, cyclical vision. The universe is not a one-time performance, but an eternal dance of creation and renewal. The beginning and the end are not opposite poles, but are intimately connected, one flowing into the other in a seamless, cosmic loop. The stardust that makes up your body may not just be from this universe. It could be the recycled ashes of a cosmos that lived and died long before our own time began. You are not just a child of the Big Bang. You may be a child of an endless lineage of universes, a fleeting, beautiful thought in a mind that is eternally dreaming itself into existence. This perspective shifts our sense of place. The urgency and finality of our single timeline dissolve into a more peaceful, rhythmic pulse. It suggests that even the ultimate death of our universe by heat or expansion is not an end, but a necessary rest, a quiet fallow period before the next spring of creation. Our existence is but one season in an infinite year. The story of the cosmos, in this view, is a poem that is constantly being erased and rewritten, each time with the same letters, but in a new and beautiful order. Section 6: Colliding Worlds. The idea of a cyclical universe, one that is born from the ashes of its predecessor, offers a profound sense of continuity, a cosmic rhythm that soothes the mind. But the mechanisms for this rebirth are as varied and strange as the cosmos itself. Let us now drift away from the vision of a universe collapsing and bouncing on its own, and explore a different, perhaps even grander possibility. Imagine our universe is not the entirety of existence. Imagine it is just one thin, fragile membrane, a brain for short, floating in a higher dimensional space we cannot perceive, a vast arena known as the bulk. And in this bulk, we are not alone. There are other brains, other parallel universes, drifting silently through the higher dimensions like great, ethereal sheets of fabric in an unseen wind. This is the strange and beautiful landscape of M-theory, a complex and ambitious candidate for a theory of everything that attempts to unite all the forces of nature. Within this framework, a new story for our cosmic origin emerges, a model known as ekpyrotic or cyclic cosmology. The word ekpyrosis comes from the ancient Stoic philosophy, meaning conflagration or a great fire. But in this modern telling, the fire is not one of destruction, but of creation. It proposes that our Big Bang was not the result of a singularity expanding from a point, but rather the consequence of a gentle yet universe-shattering collision between our brain and another. Picture it in your mind. Two vast, parallel universes, our own and another, have been drifting apart for eons. They are cold, empty, and nearly static, having expanded to their limits. But they are not free. A force, perhaps a form of gravity that acts across the higher dimensions, begins to slowly, inexorably, pull them back toward each other. Over unimaginable stretches of time, they drift closer. The space between them shrinks. The silence of the bulk is pregnant with anticipation. And then they touch. This is not a violent, chaotic crash in the way we might imagine two objects colliding in our own space. It is a soft, uniform contact across their entire surfaces. A cosmic clap, a gentle, universe-wide kiss. At the moment of this collision, the immense kinetic energy of the two moving brains is released. That energy is transformed, in a flash of pure potential, into the hot, dense, and uniform sea of matter and radiation that we recognize as the state of our universe just after the Big Bang. The collision itself is the Big Bang. It is the spark. It provides the heat, the particles, the very stuff of our reality. From that moment, our brain, our universe, begins its own journey. It is now hot and energized, and it begins to expand, cool, and evolve according to the laws of physics we know. The particles clump together to form atoms. The atoms gather to form stars and galaxies. Life on at least one small, rocky planet emerges and begins to wonder about its own origins. All of this, the entire sprawling 13.8 billion-year history of our cosmos, is just the aftermath of that single, momentous touch in a higher dimension. What makes this model so compelling to many physicists is that it elegantly sidesteps some of the most difficult problems of the standard Big Bang theory. It naturally explains, for instance, why the universe is so uniform and flat. The collision of two vast, mostly flat brains would naturally produce a new universe that is also flat and uniform. It doesn't require the special mechanism of cosmic inflation to smooth everything out. The smoothness is a property inherited from the parent brains. Furthermore, the ekpyrotic model avoids the problem of the initial singularity. There is no point of infinite density. The universe has a finite temperature and density at the moment of collision, and our known laws of physics can, in theory, describe the event without breaking down. And the cycle continues. After the collision, the brains do not merge or stick together. They pass through each other or rebound and begin to drift apart again. Our universe, now energized, continues its long, slow expansion. Over trillions of years, it will grow cold and dark once more. The stars will burn out. The black holes will evaporate. It will return to a near-empty state, a quiet, stretched-out membrane. And all the while, the force in the bulk will be working, slowly pulling it back for another rendezvous, another collision, another Big Bang. This vision of reality reframes our place in the cosmos in a profound way. Our entire universe, with its billions of galaxies and trillions of stars, might be nothing more than a single transient ripple on the surface of a much larger, higher-dimensional pond. We are living in the echo of a collision between worlds we can never see. The laws and properties of our universe might have been set by the specific conditions of that impact. A slightly different angle of collision, a slightly different energy, and the resulting universe could have been entirely different, perhaps with no capacity for life at all. This is, of course, a speculative idea. It lies at the very frontier of theoretical physics, and it is incredibly difficult to test. However, scientists are actively looking for potential evidence. A collision of brains might produce a very specific pattern of gravitational waves, primordial ripples in spacetime that could, in principle, be detected by future, more sensitive observatories. These sounds from the Big Bang would be different from the ones predicted by inflation, offering a way to distinguish between the two stories of our origin. So let your mind rest in this ethereal vision. You are not just a collection of stardust floating in a single, isolated cosmos. You might be a resident of a world born from the touch of another. Your existence is a note in a grand, cyclical symphony played out across dimensions you cannot perceive. The warmth you feel from the sun, the ground beneath your feet, the very air you breathe, all of it is the lingering energy of a collision that happened long ago. A quiet memory of two worlds meeting in the dark. The universe is not a lonely island, but part of a vast, unseen archipelago. And the tide that governs the motion of these worlds is still flowing, pulling our universe slowly, silently, toward its next creative fire. Section 7, A Universe from Nothing. We have journeyed through cosmic stories of lineage and inheritance, of universes born from the echoes of a past, either in a great cycle of rebirth or from the gentle collision of higher dimensional worlds. These are comforting narratives, for they give our universe a history, a cause, a sense of belonging to something that came before. They fulfill our deep-seated intuition that something cannot come from nothing. But now we must be brave. We must be quiet. And we must be willing to entertain a possibility that is stranger, more profound, and perhaps, in its own way, more beautiful than any other. What if our universe needed no parent? What if it required no prior cause? What if our entire, vast, and complex cosmos, with its intricate laws and its endless dance of matter and energy, truly and magnificently, came from absolutely nothing? This idea feels like a violation of the most fundamental rule we know. It is the one piece of wisdom our parents gave us, the one principle that seems to govern every aspect of our lives. There is no such thing as a free lunch. To get something, you must start with something. But the rules of our everyday world, the classical, intuitive logic of cause and effect, begin to fray and dissolve when we approach the strange and ghostly realm of quantum mechanics. And it is here, in the bizarre physics of the very small, that a loophole in reality itself might just exist. Let us first reconsider our idea of nothing. In our minds, we picture nothing as a perfect void, a dark, inert, and featureless emptiness. But in the language of quantum physics, true, absolute nothingness does not exist. What we might call a vacuum, the lowest possible energy state, is not empty. It is a seething, shimmering sea of potential. It is a silent, ghostly fizz of energy, where fundamental fields are constantly fluctuating. From these fluctuations, pairs of virtual particles, one matter, one antimatter, can flicker into existence from the void. They exist for an immeasurably brief moment, borrowing a tiny bit of energy from the future, before they annihilate each other and pay the energy back, vanishing without a trace. The vacuum of space, at its most fundamental level, is alive with this constant, silent hum of creation and annihilation. Nothing, it turns out, is a very busy place. This strange property of the quantum vacuum is the first clue. The second, and perhaps the more crucial one, comes from a simple yet profound question about our universe as a whole. What is its total energy? The answer, according to a startling hypothesis, might be precisely zero. This is the concept of the zero-energy universe, and it is the key to getting a cosmic free lunch. How can this be? Look around you. You see matter, you feel the warmth of light, you exist as a complex bundle of energy yourself. Surely the universe is full of positive energy. And it is. Every particle, every star, every galaxy contributes a massive amount of positive energy to the cosmic ledger. But there is another kind of energy in the universe, one that we often overlook: the energy of gravity. In physics, the gravitational field created by objects has a negative potential energy. Think of it like a debt. To pull two objects apart against their mutual gravitational attraction, you have to add energy to the system. Conversely, when objects are bound together by gravity, they exist in a state of negative energy relative to being infinitely far apart. The zero-energy hypothesis proposes that the immense positive energy of all the matter and radiation in the universe is perfectly and exactly balanced by the immense negative energy of the gravitational field that binds it all together. Imagine you are standing on perfectly flat ground. You decide to dig a hole, piling the dirt up into a mound beside it. The mound of dirt has a positive height, a positive mass. But the hole has an equal and opposite negative height, a deficit of mass. The net change to the total amount of ground is zero. You have created both a mound and a hole, but the overall balance is unchanged. The universe, in this view, is that mound of dirt. Gravity is the hole. The total energy might add up to nothing. If the net energy of the universe is zero, then you do not need to violate the fundamental law of conservation of energy to create it. You can, in theory, create a universe from nothing without breaking any rules, because in the grand cosmic balance sheet, you are creating nothing at all. It is simply a beautiful and complex rearrangement of zero. Now, let's put these two ideas together: the energetic, fluctuating quantum vacuum and the possibility of a zero-energy universe. The story goes something like this. In that primordial state of nothing, that timeless, spaceless quantum FOMA random quantum fluctuation could have occurred. A tiny pocket of the vacuum could have spontaneously fluctuated into a state with a huge amount of positive energy, creating a small, dense, hot universe. This would normally be impossible, a violation of energy conservation. But if, at the exact same moment, an equal amount of negative gravitational energy was also created, the books would remain balanced. The universe could spring into existence as a tiny, self-contained bubble of perfectly balanced positive and negative energy. And once this tiny universe fluctuation exists, even for the briefest of moments, the process of cosmic inflation, which we explored earlier, can take hold. The inflaton field can grab this nascent reality and expand it exponentially, blowing it up to the colossal scales we see today. The universe, then, is a quantum fluctuation that got away, a cosmic accident of the highest order. Let your mind rest in this astonishing thought. Our entire cosmos, in all its grandeur, may have begun as a random, uncaused flicker in an eternal void. It needed no creator, no prior universe, no external spark. It is a universe born of silence, a brute fact of quantum probability. This is, in many ways, the most humbling of all origin stories. It suggests that our existence is not the result of a grand design or an inevitable cycle, but of a spontaneous, improbable, and utterly natural miracle of physics. We are the children of a quantum leap. The breath you are taking now, the warmth in your body, the consciousness that is experiencing this thought, all of it, the entire magnificent tapestry of reality, may be nothing more than an elaborate and beautiful form of zero. It does not make our existence any less real or any less meaningful. If anything, it makes it more precious. We are the improbable exception, the beautiful structure that arose from a formless potential. We are a universe that, against all intuitive odds, willed itself into being, simply because the laws of quantum mechanics allowed for the possibility. We are a thought that appeared, unbidden, in the silent mind of nothingness. Section 8a, Shadow on the Wall. We have explored the grand and the infinitesimal, from universes colliding in higher dimensions to the delicate quantum flicker that might have sparked our own reality from nothing. Each of these stories offers a different perspective on our cosmic origins. But now, let us drift into a theory that challenges not just the how of our universe's birth, but the very what of its existence. It is a concept so strange, so counterintuitive, that it sounds like it was lifted from the pages of a science fiction novel. And yet, it is a serious and profound idea born from the most rigorous parts of theoretical physics, particularly the study of black holes. This is the holographic principle. The idea is as simple in its statement as it is staggering in its implications. Our entire three-dimensional universe, everything you can see, touch, and feel, the stars, the galaxies, yourself, this moment might be nothing more than a projection. A complex, vibrant, and utterly convincing illusion, like a hologram, whose information is encoded on a distant, two-dimensional surface at the edge of the cosmos. To begin to understand this, we must first return to black holes. As we've discussed, black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape. For decades, they were treated as simple, information-destroying objects. But in the 1970s, physicists like Jacob Bekenstein and Stephen Hawking made a startling discovery. They found that black holes have entropy. Entropy is a measure of disorder, or more precisely, the amount of information that a system can hold. A book with its ordered letters has low entropy. A pile of ash has high entropy. The fact that black holes have entropy means they store information about everything that falls into them. But here is the truly bizarre part. One would intuitively expect the information storage capacity of a three-dimensional object, like a black hole, to be proportional to its volume. The bigger the volume, the more information it can hold. But Bekenstein and Hawking found that the entropy of a black hole, its total information content, is not proportional to its volume. It is proportional to the surface area of its event horizon, that two-dimensional boundary of no return. It was as if all the information about the three-dimensional inside of the black hole was somehow written or smeared across its two-dimensional surface. A 3D reality was being described by a 2D boundary. This strange finding was the first major clue. It was a mathematical whisper from the universe suggesting that perhaps information is fundamentally two-dimensional. This idea was later formalized and given a solid mathematical footing by physicists Gerard T. Hooft and Leonard Susskind. They proposed that this principle might not just apply to black holes, but to the entire universe. This is the holographic principle. It suggests that there is a fundamental limit to the amount of information that can be contained within any given region of space, and that this limit is determined not by the volume of the region, but by its surface area. Let's use a gentle analogy. Imagine you have a digital movie. All the information that creates the three-dimensional world of the film, the characters, the scenery, the actioni stored as a two-dimensional pattern of ones and zeros on a Blu-ray disc or a hard drive. When you play the movie, your screen projects this 2D information into a convincing 3D experience. The holographic principle suggests that our universe might work in a similar way. The real physics, the fundamental code of reality, might be happening on a distant 2D surface that surrounds our cosmic horizon. And what we experience as our three-dimensional universe is the projected holographic image of that underlying 2D reality. You are not the three-dimensional being you perceive yourself to be. You are a complex pattern of information projected from a distant boundary. The space between your hands is not truly empty three-dimensional space. It is part of the projection, an illusion of depth created by the interplay of information on a flat surface far, far away. This idea is deeply unsettling to our intuition. Feels wrong. We feel solid. The world feels real. But our senses have been fooled before. We once felt that the earth was flat and stationary. We feel that time flows at a constant rate for everyone. We now know these are illusions of our limited perspective. The holographic principle is perhaps the grandest of these potential illusions. What does this mean for the origin of the universe? It reframes the question entirely. If our universe is a holographic projection, then the Big Bang might not have been a 3D event at all. It might have been a 2D event on the screen at the edge of the cosmos. The beginning of our universe would be the moment the projection was turned on, the moment the information began to be written onto that distant boundary. The laws of physics, the properties of particles, the very nature of spacetime would all be features of this underlying holographic code. The search for this holographic nature of reality is an active area of research. One of the most promising connections comes from a specific mathematical duality known as the ADS/CFT correspondence. It shows a precise mathematical equivalence between a theory of gravity in a 3D space, anti-de Sitter space, and a quantum field theory without gravity on its 2D boundary. This duality is a powerful tool, a kind of Rosetta Stone that allows physicists to translate difficult problems in gravity into simpler problems in quantum mechanics, and vice versa. While our universe is not exactly an anti-de Sitter space, this correspondence provides strong evidence that a holographic description of reality is a mathematically sound possibility. Some scientists have even looked for experimental evidence. They have searched for a fundamental blurriness or pixelation in spacetime, a sign that our reality is not continuous, but made of discrete units of information, like the pixels on a screen. So far, no such evidence has been found, but the search continues. As you lie here, floating in the quiet space of your own mind, allow yourself to play with this idea. The world around you, your room, the bed you are resting on, the air you are breathing it is all a projection. A beautiful, coherent, and incredibly persistent hologram. Gravity itself, that most fundamental force that holds you to the earth, might not be a force at all, but an emergent property of the quantum interactions happening on that distant 2D surface. It is the illusion of pull arising from the deep informational grammar of the cosmos. This does not make your experience any less valid or real. The hologram is your reality. The joy, the sorrow, the love, the wonder, all of it is part of the projection. But knowing that there may be a deeper, simpler, and stranger reality underlying it all adds a new layer of mystery and awe to our existence. It suggests that the universe is not what it seems, that we are, in the most literal sense, shadows on a cosmic wall, figures in a story being told by a reality we can never directly touch, but can only infer from the beautiful, flickering images it projects all around us. We are the dream of a two-dimensional world. Section 9: The Universe as Observer. We have journeyed to the edge of time and space, considered universes born from cycles, from collisions, from nothingness, and even as projections from a distant two-dimensional screen. Each of these stories attempts to explain the origin of the physical universe, the stage upon which the drama of existence unfolds. But now, we must turn to the most mysterious player in the cosmic story, a player so intimately familiar to us that we often overlook its profound strangeness. Consciousness. What if the universe is not just a collection of mindless matter and energy governed by impersonal laws? What if, in some deep and fundamental way, the universe required an observer to come into being? This is a path that takes us from the firm ground of physics into the misty, contemplative landscape of philosophy and metaphysics. It is a question that challenges the very foundations of our scientific worldview, which typically assumes an objective reality that exists independently of any mind. The idea that consciousness might play a role in the creation of the cosmos is ancient, echoing through mystical and spiritual traditions for millennia. But surprisingly, it also finds a strange and tentative foothold in the bizarre rules of quantum mechanics. As we have touched upon, the quantum world is a place of potential and probability. A particle, like an electron, does not have a definite position or a definite velocity until it is measured. It exists in a superposition of all possible states at once, described by a mathematical entity called a wave function. It is everywhere and nowhere. It is only when an act of observation or measurement occurs that the wave function collapses and the particle snaps into a single, definite state. Reality at the quantum level seems to be a participatory affair. It is as if the universe holds its breath, waiting for an observer to look before it decides what to be. This is the famous measurement problem, and it has haunted physicists for a century. What constitutes an observation? Does it require a conscious mind? Or can any interaction with a macroscopic object, like a Geiger counter, collapse the wave function? This question was famously explored by the physicist John Archibald Wheeler, a brilliant and poetic thinker who was not afraid to ask the most profound questions. Wheeler proposed a radical and beautiful idea he called the participatory anthropic principle. His reasoning went something like this: the universe, as we've seen, evolved from a quantum state. The early cosmos was a sea of quantum fluctuations, a realm of pure potential. According to quantum mechanics, the history of a particle is not fixed until it is observed. An observation made today, on a photon that has traveled for billions of years from a distant galaxy, can retroactively define the path that photon took. The act of looking, in the present, seems to reach back in time and solidify the past. Wheeler took this idea to its ultimate conclusion. What if this applies not just to a single photon, but to the entire universe? He proposed that the universe, in its early quantum state, existed as a vast superposition of all possible histories, all possible laws, all possible realities. It was a cosmic cloud of undecided potential, and it remained in this state until billions of years later, on at least one small planet, life evolved to a point of self-awareness. When the first conscious observer turned our minds and our instruments toward the heavens and looked back at the cosmic dawn, we performed the ultimate act of measurement. In this view, our observation of the universe in the here and now is what collapsed the cosmic wave function. It is what selected our specific history from the infinite menu of possibilities. It is what made the universe real. The universe, according to Wheeler, is a grand, self-observing system. It grows from a quantum seed, evolves over eons, and eventually gives rise to observers who, by looking back at its origin, grant it a concrete existence. The past and the present, the observer and the observed, are locked in a timeless, self-creating loop. This is a staggering thought. It turns our entire conception of causality on its head. We are not just the late-arriving products of a pre-existing universe. We are, in a very real sense, the co-creators of its past. We are the universe's way of knowing itself. The stars do not just create us. We, by observing them, create the stars. This idea is, of course, highly speculative and not a mainstream scientific theory. It is a philosophical interpretation of the strange mathematics of quantum mechanics. Many physicists would argue that consciousness is not required for the wave function to collapse, that any classical interaction will do. And yet, the idea persists because it speaks to a deep intuition that our own inner world of experience, our consciousness, is not just a random, insignificant byproduct of a mindless universe, but is somehow woven into its very fabric. Let your mind float with this possibility. Imagine the universe as a vast, unwritten poem, a superposition of all possible words and all possible meanings. It exists as pure potential until a read-era conscious mind opens the book and reads it. The act of reading is what gives the poem its form, its beauty, its reality. You, as you lie here thinking these thoughts, are that reader. Your consciousness is the act of observation that brings the cosmos into sharp focus. This perspective offers a different kind of answer to the question of what came before the Big Bang. In this framework, there was no before in the classical sense, but there was a state of pure, unobserved quantum potential. And this potential only became our specific reality, with its specific laws and history, at the moment when the universe became aware of itself through us. We are the universe's memory. We are the final, necessary ingredient that turns a quantum probability into a concrete history. This is not to say that the universe did not exist before humans. It is to say that its history was not fixed until it was observed. The moon is still there when no one is looking, but its quantum past, its path through space-time, is a fuzzy cloud of possibilities that is only solidified when its light strikes a conscious eye or a scientific instrument. As you rest in the deep, quiet space of the night, consider the weight of this idea. Your mind, your simple act of being aware, might be part of a cosmic feedback loop that spans billions of years. You are not just looking at the stars. You are participating in their existence. You are a tiny fragment of the universe that has woken up and, by doing so, has given a story to the whole. You are not a stranger here. You are the means by which the universe tells its own tale. The silence of the pre-cosmic void was not broken by a bang, but by the first quiet thought of an observer, a thought that echoed backward through all of time and gave the universe a reason to be. Section 10, the final, first spark. We have journeyed to the furthest shores of scientific thought, exploring the origins of our universe through the lenses of cycles, collisions, quantum fluctuations, and even the profound mystery of consciousness. Each story offers a different path to our beginning. But now let us take one final gentle step. Let us travel not to the beginning of time, but to its very end, to the cold, dark, and silent future that awaits our cosmos. For it is here, in the story of the universe's ultimate fate, that we might find the most poetic and unexpected clue to its birth. The end and the beginning, it turns out, might be the same. Let us drift forward in time, far, far beyond the lifespan of our sun, beyond the age of stars, into an era so distant it is almost beyond comprehension. This is the degenerate era, a time hundreds of trillions of years from now. The last star has flickered and died. The universe is no longer filled with the vibrant light of fusion. It is a vast, cold, and dark expanse, populated only by the quiet, fading embers of stellar death. Black dwarfs, neutron stars, and the silent, gravitational sentinels, black holes. The galaxies have dissolved, their stellar remnants drifting apart in the ever-expanding darkness. It is a universe of shadows and ghosts. But even this is not the end. Time continues its slow, relentless march. Over a period of time so vast it makes the current age of the universe seem like a fleeting instant. Even the black holes, those most stable of all cosmic objects, will begin to die. As we have learned, through the subtle magic of Hawking radiation, black holes slowly lose mass, emitting a faint, almost imperceptible glow. The largest supermassive black holes, the anchors of long-dead galaxies, will be the last to go. They will persist for an unimaginable duration, perhaps up to 10 to the power of 100 Google years. They are the final, silent keepers of the universe's light. During this black hole era, they will be the only significant structures left in the cosmos. But one by one, over eons that defy description, they too will evaporate, returning their locked-up energy to the void. Each one will end not with a bang, but with a final gentle sigh, a last whisper of heat as it vanishes completely. And what is left then? The universe enters its final state, a state physicists call heat death. It is a cold, dark, and perfectly uniform sea of fundamental particles, mostly photons and neutrinos, spread thinly across a space so vast it is effectively infinite. There are no structures, no stars, no planets, no life. There are no energy gradients left to power any process. Entropy, the measure of disorder, has reached its absolute maximum. Everything that could happen has happened. The universe has reached a state of perfect, eternal, and unchanging equilibrium. It is a reality that is functionally indistinguishable from nothingness. The cosmic story, it seems, has come to a final silent end. Or has it? It is here, at the very end of time, in this state of near-perfect nothingness, that a familiar idea reemerges. This cold, empty, and uniform state of the distant future bears a striking resemblance to another state we have visited on our journey. The timeless, spaceless, and uniform potential that existed before the Big Bang. Let us return to the radical and beautiful idea proposed by Sir Roger Penrose in his conformal cyclic cosmology. He argues that in this far future universe, where only massless particles like photons remain, the concepts of time and distance become meaningless. A photon does not experience the passage of time. From its perspective, its entire journey across the cosmos is instantaneous. Without massive particles to act as clocks or rulers, the universe loses its sense of scale. It becomes conformally invariant. And here is the heart of the cosmic poetry. Penrose suggests that this cold, infinitely vast, and scale-free future of one universe is mathematically identical to the hot, infinitely dense, and scale-free state of a Big Bang singularity. The end of one cosmic aeon smoothly and elegantly becomes the beginning of the next. The final state of the old universe, having forgotten all its structure and scale, provides the perfect, simple starting conditions for a new universe to be born. The final, fading whisper of the last evaporating black hole is, in a sense, the first spark of the next Big Bang. The cycle is complete. The cosmic serpent eats its own tail. The end is the beginning. Our Big Bang was not the first, and the ultimate death of our universe will not be the last. It is part of an eternal, magnificent sequence of creation, evolution, and renewal. Each universe is born from the ashes of the one before, carrying within it the faint, ghostly echoes of its parent, but free to write its own unique story. This is a vision that unifies the grandest scales of time. It suggests that the universe has no ultimate beginning and no ultimate end. It simply is forever transforming, forever becoming. The question, what came before the Big Bang, is answered in the most beautiful way imaginable. Another universe. A universe that lived its long and glorious life, faded into a quiet sea of light, and then, at the very end of its story, became the seed for our own. As you lie here, resting in the final moments of our journey, let your mind embrace this grand, cyclical vision. The matter that makes up your body, the consciousness that is experiencing this story, is not a one-time accident in a lonely cosmos. It is a part of an eternal rhythm, a timeless pattern of death and rebirth. You are a fleeting, precious note in a symphony that has been playing forever and will continue to play forever. We began our journey at the edge of knowing, staring into the mystery of what came before time. And we have arrived here, at the end of time, only to find ourselves looking back at a new beginning. The universe is not a straight line, but a circle. The final spark of one reality is the first spark of the next. There is no ultimate cause because the cause is also the effect. It is a self-creating, self-perpetuating, and utterly magnificent loop. The greatest mystery of our origin may be that there is no origin, only an endless, beautiful transformation. The story never truly ends. It just begins again. And so, we return from the edge of time, having drifted through the quiet, speculative spaces where science and philosophy meet. We have asked the deepest of questions and found not a single simple answer, but a beautiful tapestry of possibilities. Our universe may be a chapter in an eternal book, a ripple from a collision between worlds, a flicker in a quantum void, or a dream that we ourselves helped to create. Perhaps the most beautiful truth is that we do not yet know. The mystery remains, and it is in that mystery that wonder finds its home. The silence before the Big Bang is not an empty silence. It is filled with the quiet hum of potential, a gentle invitation to keep asking, to keep dreaming, and to keep looking up. Good night, and may your rest be as peaceful as that primordial stillness.